the divergence theorem is the theorem that gives us an alternative for calculating flux integrals. Flux integrals, by definition, can be calculated as a surface integral across a surface. The divergence theorem applies when I have a simple solid region and S is the boundary of that region oriented out. If S is not the boundary of a simple solid region, the divergence theorem does not apply. And in order to be the boundary of a region, it has to fully enclose that region. Okay. So on exam 3, you had a situation where you had the top half of a sphere. That's not the boundary of a simple solid region because it's not fully enclosed. It has no bottom surface to it. Okay. So if it fully encloses things, you want to imagine that, let's say I took this and I turned it upside down and filled it with water and then I put it back in this orientation. The water would not stay in. It would fall out because it's not fully enclosed. Okay. So it's got to be like a cup with a cap on it, or the full sphere that would fully enclose that region. Okay. If you have that, and it does need to be oriented out, so sometimes that necessitates checking that you have the correct orientation, but then if you have that, the flux of F across S is simply the triple integral over that enclosed region of the divergence of F. Okay. Now, that can be very nice, particularly if you have that the boundary is a piecewise smooth thing, so that you'd have to do several integrals. Or if the boundary were the entire sphere, because I can parameterize the entire sphere, since rho is constant, I can use the other two spherical coordinates, theta and phi, as my parameters. But that's a little bit cumbersome to work with. It's certainly doable, but very often the divergence theorem makes things a little bit faster. But gotta make sure that I only use that if I actually have the boundary of a finite solid. Now, if I were evaluating the flux across this, which is not the boundary of a finite solid, I could say that if I included this disk on the bottom, so if I said this was S1 and this disk on the bottom is S2, and S1 plus S2 together are the boundary, the piecewise smooth boundary of the solid half sphere that would be enclosed between them, the divergence theorem would apply over that. So I would know that the flux over S1 plus the flux over S2 is the triple integral over the enclosed region of the divergence of F. Then I could, if I wanted to, say the double integral along S1 of F dotted with N ds would be the triple integral over E of the divergence of F dV minus the flux across S2. Because these two things added together would equal this. So if I have a surface and it's not the boundary of a simple solid region, I could add to it so that I'm completely enclosing things, and then I could use the divergence theorem. Now, it's not clear to me that there are a lot of situations where this is going to be faster than simply evaluating the surface integral to begin with, but there are certainly times when both of these integrals would be very, very simple, and this integral would be a lot more complicated. So that is an option, but simply applying the divergence theorem to a surface that's not a boundary of a finite solid is not okay. And I'm emphasizing this because that can take a problem where I was trying to test you on a particular skill and make it way easier. And so not only is that a big conceptual problem that you misapplied a crucial theorem in calculus, so that's automatically going to be several points off, but sometimes that robs you of the opportunity to do the more complicated problem and earn the points that I had allocated to that. So it's something you want to be very, very careful of, because there were a number of people who lost a significant number of points on exam 3 by misapplying this theorem. So it's a lovely theorem. It's wonderful. You should absolutely know how to use it. You might be required to use it, but just be cautious. It does have this condition. make sure that that condition is satisfied before you use the theorem.